In this video, we're verifying solutions of differential equations and looking at Euler's method. So first off, let's verify the solutions of the differential equations. So we have an equation right here for which we need the first and the second derivative, so let's go ahead and take some derivatives. So over here we get 2 times the cosine of 4x times the derivative of the inside, because this is a chain rule. We get 8 cosine of 4x when we simplify. Double derivative, we get 8 times the negative sine of 4x times the derivative of the inside. So simplified, we have negative 32 times the sine of 4x. Plug it into our equation to see if it works. We can simplify it a little bit and get down to negative 16 sine of 4x, because we have negative 32 plus 16. And over here we have 48 cosine of 4x. We can factor out a negative 16, which leaves us with sine of 4x plus 3 cosine of 4x, which that is not going to be equal to 0. So that equation is not a solution of the differential equation. Let's try the same thing over here. First derivative, move the derivative of the 2x down, so that means we get 6 e to the 2x. Second derivative, same thing, 12 e to the 2x. Plug them in. So we have 12 e to the 2x minus 36 e to the 2x plus 24 e to the 2x, which if we add these together we get 0 equals 0, so yes, this one does work. And letter C, oops, not what I wanted to do. We're going to take the derivative first. The c is a constant, so it works just like the number 3 up here or the 2 in the previous one. So this time we get 4c e to the 2x, and the double derivative we have 16c e to the 4x. Plug it in. We have 16c e to the 4x minus 24 e to the 4x, oops, plus 8c e to the 4x, which if we add these together does give us 0 equals 0, so this is a yes as well. Alright, and then we've got Euler's method here. So we have a differential equation, and y of 0 equals 3. We want to find the approximation for y equals 1 by using that Euler's method. So 1a, we have dy over dx, which is our slope, is x plus 2, and y of 0 equals 3. So we can set up a table. We've got x, y, and dy over dx. So for the first one we have 0, 3. If I plug that into here, my slope ends up being 2, which means I can write the equation like this. So then for my next one, which I'm going to use a half, because we want to get there with 2 equal steps, so a half and then 1. So if I plug in a half into this equation, I get 4 for y. Plugging a half into this up here to find my slope, I get 2.5. So my new equation is y minus 4 is equal to 2.5 times x minus a half. Plugging in the 1 into this equation, I get 5.25. So that means y of 1 is 5.25. Now it wants me to solve the differential equation and use that differential equation to find my solution. So for 1b, we still have dy dx equals x plus 2. We still know that y of 0 equals 3. So let's separate this. So we're going to move the dx to the other side. We're going to integrate both sides. So we get y is equal to the integral of this. So 1/2 x to the second plus 2x plus c. We have to find c, which means we're going to plug this into our equation here. So 3 is equal to 1/2 times 0 squared plus 2 times 0 plus c. So c equals 3. So my equation is y equals 1/2 x squared plus 2x plus 3. Plug in the 1. And my answer is 5.5. Now for part C, I want to find the error using the Euler method is the difference between the approximate value and the exact value. What was the error in your answer? How could you produce a smaller error using Euler's method? So first of all, let's find the error. So Euler's method minus the actual value, which gets me, and we're going to take the absolute value of this, so it gets me the absolute value of negative 0.25 or 0.25. That is our error. Now we want to see if we could, or how could we possibly, get a smaller error. Now up here, we used 2 steps to get to 1. If I use more steps, would my error technically get smaller? Well, if you have a parabola, and we know this value, and we want to find this one, and I use 2 steps, my 2 steps could have quite a bit of error. If I use more than 2 steps, I could get closer to the curve, meaning my error would be smaller. So if we use smaller steps, then we produce a smaller error. And that is it.